Raphaël Cosson. I'm a PhD student supervised by Bilel Derbel, and I work with him, but also with Arnaud Liefooghe, Hernán, Aguirre, Kiyoshi, Tanaka, and Qingfu Zhang on this paper, Decomposition-based Multi-Objective Landscape Features and Automated Algorithm Selection. So as the title says, this work is about multi-objective optimization, but also landscape analysis and decomposition. So first, I will present a minimal background about those three notions. Multi-objective optimization is when we try to optimize, usually minimize or maximize a fitness function, which returns two or more values. As motivation for such problems, many real-world problems, in fact, are multi-objectives. One of the characteristics of multi-objective optimization problem is that a solution can dominate or be dominated by another solution. So if all fitness value for each objective of a first solution is greater or equal than another solution, then this solution dominates the solution with lesser value. And two solutions which do not dominate each other are said to be incomparable. Actually, in multi-objective optimization, we don't seek to find one optimal solution, as most of the time there is not only one solution, but instead we search for the set of non-dominated solutions, which is called the Pareto front. There actually exist several evolutionary optimization algorithms, such, for example, as the framework MOEA or NSGA. But those algorithms have many components and parameters, and such components and parameters alter their efficiency. There is not one algorithm which can outperform all other algorithms for all problem instances. But instead, given a problem instance, we can find one algorithm or one configuration of an algorithm which will perform better than the other. So we can ask two questions. What makes a problem instance challenging for an algorithm? And how do we choose the most efficient algorithm for a problem instance? In our work, to answer to this question, we are interested in a landscape-oriented approach. So landscape analysis is a way to understand the structure of what we call the landscape of the optimization problem. We construct, in fact, a space given a notion of distance between solutions, and by measuring the fitness, we are able to recreate a space. And using this, we can, from sample of solutions, approximate the geometrical structure of the problem. So landscape analysis is not only useful to have a fundamental understanding of the structure, but we can also extract numerical features, which are numerical approximation of the structure. And using those features, we can perform an algorithm selection task or an algorithm configuration task. So this idea was first introduced by Spearman in exploratory landscape analysis, and later used for algorithm selection. So as you can see in this figure, to perform an algorithm selection task, we need first a set of algorithms, a set of problem instance. We'll need to know the performances of algorithm over the problem instance. We then, in the meantime, compute features, landscape features for each problem instance. And then we can try to predict algorithm performances given the features of a problem. And the goal is that if a new problem came up, you can just compute features and then predict which algorithm would be the best performing to solve it. However, landscape analysis has been mostly studied for single objective optimization. There are few existing multi-objective features based on dominance or indicator, but here in this work, we are interested on how can we use previous single objective landscape analysis work, but this time for multi-objective optimization problem. So the contribution that from this paper can be divided in 3 parts. First, we propose a methodological way of computing multi-objective features using decomposition. Then we study the 2 features and their relationship with the benchmark landscape that we use. And finally, we perform an automatic selection task to predict the best performing algorithm given a problem instance and using always our previous decompose-based features. So first, what is the approach that we propose? Decomposition is a strategy that we can find in many multi-objective algorithms, in particular in the framework MOEA, and it's aimed at transforming a multi-objective problem into a number of single objective sub-problems. So given a scalar function and weight vectors, we'll decompose in this example, it's a two objective multi-objective problems. We'll decompose this multi-objective problem into a number of single objective sub-problems. So a solution of not only its multi-objective fitness from the original multi-objective problem, but also a single objective fitness for each sub-problems. And by using decomposition, we propose to decompose to compute landscape features landscape to perform a landscape analysis on a multi-objective problem. We propose to decompose a multi-objective problem into single objective sub-problems. Then for each sub-problems, we'll compute a sample of solution fitness over the sub-problems, single objective fitness. And using this sample, we can compute single objective features. We'll do the same for all sub-problems. And finally, once we have the set of single objective features, we can aggregate them using an aggregation function into a new multi-objective features. So a few questions remain. How do we sample? Which single objective features do we use? And how do we aggregate them into multi-objective features? We propose to use as a sampling method random walk and adaptive walk. Random walk consists of taking one solution at random and making it evolve by a small step and repeating the process until we reach the wanted sampling size. When using random walk, only one random walk is needed to compute the features. But adaptive walk is when we make evolve a solutions when we try aiming to increase one objective. So we need to compute one adaptive walk for each features. In terms of features, we use 4 sets of features, both either from the literature or inspired by the literature. The first set is a distribution of fitness value, which consists of classical statistics about the fitness distribution. The second set is a distribution of fitness differences between a solution and its neighborhood. The third set is a proportion of fitness improving neighbor for a solution. And the fourth set is the size of the adaptive walk. And finally, to aggregate to function, we use 4 functions. To aggregate to features, we use 4 functions: the mean, the standard deviation, and the first and second coefficient of a polynomial regression. So here you can see the 108 multi-objective features, and as you can see, there is also an intermediary layer of statistics between the sampling and the multi-objective features. On the second part, we are interested in studying these multi-objective features on a benchmark landscape. So we are interested in the rMNK-landscape, which is somehow a tunable optimization, multi-objective optimization problem in which we can fix 4 parameters: the number of objectives, the dimension, but more importantly, the correlation between the objective, ρ, and the number of interaction between variables, k. So we generate a phasant problem instance using a Latin hypercube sampling and only with 2 objectives. And we compute for each of these problem instance features using mu at 20, so 20 single objective subproblems. First, we can ask, how do we, before the aggregation of our features, could they represent, do the feature, single objective feature characterize the landscape? So each figure here concerns different features, and we plot the evolution of feature value for each subproblems, and each color corresponds to a different problem instance. So problem instance in blue correspond to a parameter k epistasis at 0, green at k at 2, red k at 4, and the variation of color from blue to purple, green to cyan, and red to orange is the variation of parameter ρ from 1 to -1. So visually in this plot, we can see that there are a difference in features value between parameter k at 0, parameter k at 2, and parameter k at 4. And actually, the shape of the curve in some features is also related to ρ. So to improve to this analysis of the features, now we're interested in when we aggregate the features into a multi-objective features. We studied the relationship using by making 2 models, a random forest regression and a random forest classification, to learn respectively parameter ρ and parameter k. From this figure, so we use the Gini impurity as a measure of quality to determine which features were the most important to predict each parameter. And here only a small sample of feature is represented due to space. But what we can conclude is that, first of all, the feature useful for one parameter is not the same for the other parameter. So as you can see here, ρ mostly need only one feature. There is one feature which appears either extremely correlated or anti-correlated, and it's enough to predict it, unlike K that will need more features. But all sets of features are present. And we can see that the most important set of features for ρ is the proportion of improving neighbors, and for k, it's a proportion of the distribution of fitness differences. To complement this previous analysis, we made a Spearman correlation matrix between features and parameter ρ and k. So here again, that's a sample of features due to space. But we can see 4 distinct clusters. The first cluster is in fact extremely correlated with k, but neutral to ρ. The second cluster is anti-correlated with k, but neutral with ρ. The third cluster is anti-correlated with ρ and neutral with k, and fourth cluster is correlated with ρ and neutral with k. It's good to notice that the previous most important features for ρ appear in fact to be the most anti-correlated features with ρ. In a last part, we used this decomposition-based landscape-aware methodology, and we applied it to automatically select the best algorithm given a problem instance. So we use MOEA, which is a famous framework for multi-objective, and MOEA have several variants, several parameters. And we use both the standard MOEA, but also two other variants, MOEA-SS, MOEA-SC. So more information about this algorithm can be found in the article. And we used those three algorithms as a set of algorithms. We computed their performances over the benchmark. And we use the average hypervolume deviation as a measure of performances to decide which algorithm was the best given a problem. And with a budget of 1 million evaluation, and use a random forest regression with an 100 tree to learn from with the features in input which algorithm the algorithm performances. So the model actually takes the features in input and try to predict for each algorithm, each three algorithm, its performances. We were interested we made several experiments on this model, and in particular, we explored two different points. First, we explored the accuracy of the features given the number of sub-problems that we use. So the number of single objective sub-problems. And secondly, we also explore what happens if we do not take a uniform distribution of sub-problem when decomposing the problem to compute the features. So here, the blue box corresponds to a random distribution of sub-problems, and the brown box corresponds to a uniform distribution of sub-problems. And this is for when we increase the number of sub-problems used in the features. As a measure of quality, we use a notion which is the merit. There are also others on the article, but here we will present this one. The merit is a way to compare performances between what we call the single best solver, the best algorithm in average, the virtual best solver, the best algorithm for each problem, and the real solver, so the actual algorithm recommended by the learning model. What is good to know about this measure of quality is that when the merit is over 1, it means that using the algorithm predicted is worse than using the single best solver, so the best algorithm in average. And when we have a merit between 0 and 1, it means the closer we are to 0, the closer we are to the virtual best solver. So when we are at 0, that means the model do not make any mistake. By experiment, we concluded that first increasing the number of sub-problems allowed to improve the accuracy of the features, or at least the accuracy of the model in predicting the best algorithm using the features. However, unexpectedly, when we take only one sub-problems with a uniform distribution, it achieves good results, but we assume that this is only relative to the benchmark landscape, as the shape of the Pareto front is both convex and symmetric. Also, when we take only when we use a random distribution of sub-problems, we can see that the model lost accuracy in comparison with uniform distribution. Finally, we reach a merit of 0.29. It means that the algorithm, using the predicted algorithm is somehow 3 times better than the best algorithm in general. However, this value is without taking into account the features cost, which may reduce this good result. To summarize this work, at first we proposed a methodology to compute multi-objective features using decomposition, and we analyzed their efficiency when characterizing the rMNK-landscape benchmark. And we also analyzed their efficiency in automatically selecting the best performing algorithm. However, there are many open issues that are left. We should first begin by enlarging our benchmark settings. So what happens when we use more than B-objective optimization problems? Can we use what happened with other algorithm or other benchmark instance? Another important issues, is, as I said in the previous slide, we do not take into account the cost of the features. And finally, we are also really interested in comparing decomposition-based multi-objective features with other existing features and analyze their complementarity. Thank you for listening. If you have any question, I will answer. And in the meantime, you can see a short illustration of how algorithm performances are related to the landscape of the problem.
Okay, thank you very much, Raphael, for this interesting talk and the nice picture at the end. Okay, are there any questions? You can either type in the chat or raise your hand, and I hopefully see that. Okay, what people are thinking about their question. I have one about one of the points you had on your future work slide. You said you want to consider other algorithms, right?
That's something that can be done, yes.
So this MOEAD algorithm, that's decomposition-based, right?
Yes, MOEA is an algorithm that uses decomposition and will there is a bug. I cannot move my slide anymore. But anyway, MOEA. So the algorithm will, in fact, decompose the problem into a number of single objective subproblems, and there will be it will search to solve all single objective subproblem in parallel, and there will be interaction between each subproblems to find the Pareto front. This is the principle of MOEAD.
So in some sense, there seems to be, so the way you extract the single objective features seems to kind of be in line with how that algorithm works, right? So
actually, this algorithm was a bit of inspiration for how to compute features, but here our objective is not the same. We do not take interest on how well is functioning, how well is performing MOEAD, but we just want to compute features for multi-objective landscapes. That's the difference.
Okay, so you basically, your hypothesis is that you could also use a similar idea to then say use NSGA2 or something like this with that sort of fitness analysis, or the fitness landscape analysis, or would you need to modify the framework quite drastically?
Actually,
if you don't. Okay, that was a tough question, I guess. Sorry.
No, I think we can use algorithm. We can be inspired by algorithm to make concept of how to compute multi-objective features. But here we just want to explore what happens when we use decomposition. If we can be inspired by NSGA to make features, maybe, I don't know, but
subject to future work.
But actually, when I say also I want to test with different algorithms, is because we use decomposition-based features for to predict algorithm which are already which use decomposition in their strategy. What happens if we take an algorithm that do not use at all decomposition? It should not change anything, but that will make a panel more. So that would enlarge the panel so that it's more to convince people more easy.
Okay, I think that sounds really interesting, and I look forward to seeing the follow-up work. Manuel has another question.
Hi, Raphael. Can you hear me?
Yes.
So I was wondering, maybe I missed this, if I missed it because I was looking at other place for a couple of seconds. Did you analyze after you did the training how important are actually the features that you compute for the selection. So I guess there could be some features that they look good when you did the correlation analysis, but actually once you have trained the random forest, they don't have any effect whatsoever.
Yes, we did such analysis, and we could see that there are a variation of which feature is the most important once we do not take interest in predicting raw K, but predicting algorithm performances. However, the fourth set of features was still useful, a bit less for the size of the adaptive walk, if I remember well. It should be in the article, or maybe we did not add any more space in the article. I forgot, but what I can say about it.
I think that's enough. I could say in the article. I think it would be interesting anyway to know, because you can compute so many features and you don't know if they are going to be useful or not. So having an idea or some intuitions about this is interesting.
We'll just check the article. But I think in the article we do not show this plot about the feature importance once we
Okay. I think this.
Thank you.
There are no other quick questions. I think then we should move on to the next talk. So.